Hello everybody, and welcome to the course of Scalable Data Science. I'm Anirban, I'm from IT Gandhinagar. So today we'll be talking about two different but related algorithms. The first will be about an application of the fast Johnson-Lindenstrauss transformation to locality sensitive hashing. Okay, so here's the first slide for us. Okay, so just to recall, Johnson-Lindenstrauss transformation was this particular linear mapping that preserves the distances between any two pairs of points, in the sense that if we are given a set of points x1 to xn, right, and if I come up with a mapping A that, let's say, is either created out of independent Gaussian entries or according to the fast Johnson-Lindenstrauss transformation, which we'll recap in a moment. Right, and it's of A is of appropriate size. For instance, A is of size at least some constant by epsilon square log n, right, for a suitable constant, which happens to be pretty small in practice. And now, if I get an image of each of the points xi by multiplying it by A, right, and the xi's lie in d dimension, right, so A is of size k by d, in order for us to be able to do the multiplication. Then the Johnson-Lindenstrauss lemma claims that with a very high probability, the distance between the L2 norm between AXI and AXJ will lie within a 1 plus minus epsilon factor of the distance between xi and xj. Okay, so the lemma, as it is stated here, is about is only about existence, but as we have seen, we can claim that this will happen, that for a particular random sample of A, this happens with a very high probability. So just to recap again, what is the time taken for projection? The time taken for if the random matrix was selected out of independent Gaussian entries or from independent plus minus ones and zeros, the time taken for projection is order kd, which is basically the time taken to multiply a k by d matrix with a vector of length d, right? And remember that this k was at least 1 by epsilon square, right? In fact, it had the log n factor or the log 1 by delta factor, depending on what version. I mean, whether you want it to hold for all pairs with high probability, or whether you want to hold for a single, for every single one with probability 1 minus delta. Okay. So basically, the success probability has to come into the log. The other construction that we saw was this fast Johnson-Lindenstrauss transformation, and here I have some correction to make for the previous video. What we had mentioned is that the fast Johnson-Lindenstrauss transformation has three components, right? The first is the plus minus 1 diagonal matrix, right, where every entry of D is generated from a random coin toss that gives you plus 1 with probability half and minus 1 with probability half. Next comes the Hadamard matrix, right? And we had defined the Hadamard matrix in the form that the H2 is 1 1 1 minus 1. Right, H4 is obtained by doing H2, 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 and minus H2. Right. What we had forgotten out here was the normalization. Right, because if you had been paying attention, that we always need. I mean, in the original Johnson-Lindenstrauss, we always needed to normalize so that in expectation it becomes a matrix, so that it basically preserves the norm in expectation, right? So it is unbiased in terms of the L2 square norm. So that's why what we want to do is instead of take this particular H, which essentially is the unnormalized Hadamard matrix, and then do a 1 over square root D times H. Right? This is what we call the Hadamard matrix. This is traditionally what is known as the Hadamard matrix, that you have you create H using this recursive definition, and then you normalize it so that the length of every column is exactly 1. Okay, the L2 length of every column is exactly 1. Okay, so what we'll do is when I now onwards refer to the Hadamard matrix, it will refer to this normalized Hadamard form, and then we won't really keep this . We won't really keep this over square root D hanging around, but you have to understand that this is the normalized version of the Hadamard matrix. Okay, and finally, so the final component was this P, which was a sparse Gaussian matrix. Okay, And so the time taken was given by order d log d, which is the time taken to calculate the Hadamard transformation, plus the time taken to calculate to multiply p with the dense vector that results from hdx. Okay, and that time is k log nd because p is sparse. P has a small number of non-zero entries. Okay, so and the densification claim that we had, just to remember that, again recall that here H refers to the normalized Hadamard matrix. The densification claim that we have is that for any fixed x, right, that satisfies L2 norm 1, if you look at the maximum coordinate of h dx, that is the average coordinate is 1 over square root d, right? Because there are d coordinates and they all sum up to square summation xi square equal to 1, right? And then the d of them, so therefore in some sense the average coordinate is 1 over square root d. What this is saying is that the maximum coordinate is not much bigger than this. The maximum coordinate is log n d by square root d, right? What this implies is that the vector h dx is basically dense, right? Because if the maximum coordinate is this d by log square root nd, which means that there has to be a significant number of non-zeros, right? In some sense there has to be d by log nd non-zero entries, right? Because they have to sum up to 1. So, and this we had obtained, we had mentioned, although we had not seen the proof, as this can be obtained by some chain of style tail inequalities. Okay, fine. Let us. So, what we had seen is that calculating PHDX takes time order d plus k log nd. Now the question is that let's see an application of this, and we'll see an application in, very interestingly, in something that we've covered before in locality sensitive hashing. Okay, just to recall what locality sensitive hashing, and let's say that we right now we are doing locality sensitive hashing for the L2 distance. Okay, so let's say that so just to recall what we had done is that the ith index of a particular hash table, one hash table capital H, let's say we are talking about only creating only one hash table. One hash table is created by a k tuple h1 to hk, right? And let's talk about creating, let's say, the ith index of this, the ith value here of this tuple. So to create hi of x, we first choose a random vector vi, right? We take the dot product of the projection of x with vi, the dot product of x with vi, right? We add a shift bi, where bi is a uniformly chosen bit in the range from 0 to w for some hyperparameter w, and then we divide it by w, and then we take the floor of this. So in some sense what we are returning is this is the index of this. We have chopped off the picture, the projection into these buckets of length w, right? And then bi you can think of as giving a random shift to this chopping off, right? As in we don't really need to start at 0. We sort of add a random shift of bi and then start the chopping off, and then we return the index of the bucket into which this particular projection of x falls into. Okay. So, and we want and so the time taken to calculate each of all the k hash indices is k times d, because the time taken to calculate one of these indices is d, right? So, and therefore for all the L buckets, right, the time taken is kdl. Okay. So can we reduce this time? Right? Because if you remember reducing this time, so what is the query time? The query time for an LSH has two components, right? The query time for an LSH has a component that says that you have to calculate all the hash functions. It also has a component that says that to calculate all the hash functions and find out the bucket that the query falls into, you then get to go into the buckets and find out the candidates and compare the distance with each of the candidates. Okay, so then can we reduce this particular time? Can we at least reduce the time taken to calculate all the hash functions? And why are we talking about this? Because now we know that we have some idea of, because this kind of looks a lot like random projections, right? So, and we know of faster ways of doing random projections. So can we utilize this, right? So it's a natural question to ask. In order to formalize the algorithm, let us first draw the connection between random projections and locality sensitive hashing in the L2 case a little bit more tightly, right? And the connection is pretty intuitive, right? We can basically look at LSH as a random projection happening onto k dimensions plus a quantization happening on each of the dimensions, right? So what is happening that you can think of, remember for each of the coordinates we're multiplying the query, we're multiplying the data point x by a random vector vi. Think of creating a matrix A by just stacking these random vectors vi in the rows, right? So each row of A is one of the vi's that we were using before, right? And then think of multiplying A with the vector x. We now get a k-dimensional vector ax, right? So this is a k-dimensional vector. Now we add a random, instead of choosing a single value bi, right? Just choose one bi for each of the coordinates. Just create a k-dimensional vector with a random choice bi for each of the coordinates that lies in 0 to w, right? Then add these two. So calculate ax plus b. This is again our k-dimensional vector. Right? Now bucketize it, each of the coordinates independently, and you're done, right? You in one sort of fell swoop of a matrix vector multiplication plus some shift, and now you have the entire k-sized index for a single hash table. Okay, and this is, I'm not saying anything new, but this is what we have been doing. So the time taken by this, so the time taken remains the same because the procedure is the same, and so it's kd per hash table. Now you see the connection. Can we make this faster? Okay. So if I want to make this faster, I want to preserve some certain properties. What is it that we want to preserve? Right. So to do this, let us step back a little into LSH and see that what was the important quantity that we were talking about when we were analyzing how good of a locality sensitive hash function was this particular algorithm, right? How do we analyze the quality of a locality sensitive hash function? And if you remember, we were analyzing it by looking at the collision probability. So what is the collision probability? The collision probability in a short sort of sentence is to say that supposing 2 points are at distance u, right? P and Q are at distance u in terms of the L2 distance, and I want to see what is the probability that they'll collide. Okay, so while we have not written this down exactly in the previous discussion, for this particular construction, you can actually write down a sort of nice form for the collision probability, right? And I'll just give you an intuition for this. Right? So in the case that hi of x is this particular quantity, hi of x is this particular quantity, right? We can write down what is the probability of collision if 2 points are at distance u. Right? And the way we do this is as follows. I'll just give you an intuition for this. So remember that x times vi. So what is x times vi? Or rather p times vi versus q times vi, right? So if you look at the random variable p dot vi minus q dot vi, right, that is a Gaussian random variable, right, because of the two stability property of Gaussians that we have seen. That is a Gaussian random variable and has variance that is distributed with a standard deviation that scales with the L2 distance between p and q. Okay, so p dot vi minus q dot vi is a Gaussian variable with variance p minus q L2 p minus q distance square. Okay, so then I can actually write down what the PDF of this random variable is, right? Because suppose f of v is the PDF of the absolute value of n01, right? Therefore, the PDF of this of let's say if I multiply v by alpha, the PDF of this quantity, the PDF of the random variable f alpha v is actually 1 by alpha f v by alpha. See? So let me clean this up a little bit, and so that we can see better. So the PDF of alpha v is 1 by alpha f of v by alpha, and you can see this if you just think about it for a couple of minutes, because you are sort of in some sense multiplying by alpha is just reducing the scale, it's just changing the scale of the random variable, right? And so the standard deviation changes, and that's what is reflected here. Okay, so then what this is saying is that the probability of collision, right, that if two points are at distance u, right, this part, right, kind of measures that what is the for a particular value of t, right, what is the chance that the random variable p minus q dot vi, right, which is a random variable with this PDF, what is the total probability that p minus q dot vi lies in the range from 0 to t, okay? And this part kind of measures, right, that what is the chance that w, right, that the b, or rather the b, right, so what is the chance that b actually happens to drop a separator, happens to, remember what is b doing? B is just shifting the boundaries of these intervals, right? I mean the boundaries could start at 0, or if you add to b to everything, boundaries could start at b, right? So you can think of b as just playing around, as just randomly shifting the separators between the intervals, right? So then what this part of it is the probability that b is chosen such that a separator drops between 0 to t, right? Or rather a separator doesn't drop between 0 to t, right? Because the probability of that is that a separator drops only in this interval from t minus w to from t to w, which is of size t minus w by w, which is exactly 1 minus t by w, right? So this kind of captures the probability exactly that there is a collision between that HIP equals HIQ. It's not hard to see that this is decreasing with increasing u, okay? So now, and this is what we want to say, that even if now why is this useful? What we want to say is that if I do something other than the independent Gaussian, I want to make sure that this collision probability does not suffer, that the collision probability does not increase beyond what it was in the independent Gaussian case. Okay, this is how we are going to analyze this. So this comes from a paper of ours, Dasgupta Kumar Salas, called the AC hash, named after Eilon and Chazelle. What we say is that this is that our original sort of LSH was essentially calculating AX plus B and then quantizing each of the dimensions by using these buckets, using these intervals of size w, where A was a Gaussian n matrix. Simply replace A by the fast Johnson-Lindenstrauss matrix, which is now composed of P, then the normalized Hadamard matrix, and the diagonal matrix T. Okay, instead of the Gaussian matrix, just use P, and choose Q to be of more or less of the same type, same order as we were choosing the original Q in the FJLT construction, basically like log d by d. I mean, it's a little different, slightly different, but basically the same. Now the projection time, remember when A was Gaussian, the projection time was kd, and now the projection time becomes d log d plus k log square d, exactly the FJLT construction. Okay, so the projection time technically has improved, right? Because k is 1 by epsilon squared, and so it is potentially much less than log d for all practical values of d and epsilon. Okay. So, but that is not enough. Now we have to argue that this particular construction that we have sort of done using LSH has the same properties as the original LSH construction had in terms of the collision probability, right? And this is not an easy argument, right? Because now what has happened is that just intuitively the different sort of indices of a particular hash function, let's say if a particular hash table hx is now h1 of x times h2 of x, h1 of x and h2 of x are no longer independent of each other because of the particular projection FJLT construction that we have done. So it complicates the analysis quite a bit. But what we are now still able to say is that if you take what was it previously? So previously what we were saying that for each hi of x, right, probability that hi of p equals hi of q was p of u, if u is the distance between p and q. So therefore probability that capital H of x p equals capital H of q equals p to the k of u, right? Because remember, because a hash table is constructed out of k such hash functions that are IID, right? So therefore the probability of collision becomes pu to the power k. Okay, so then this you should think about as this basically is like the original LSH collision probability. Now what we are denoting the probability of collision of so let's say h tilde is my new hash index, which is a k bit index again. Now we define the probability that h tilde of p equals h tilde of q to be PAC of U. So now this is the combined probability that the particular k tuple that I've created for a single hash table collides with the particular k tuple for P and collides with the k tuple for Q. Okay, and we have to we cannot segregate, this is not independent all as I mentioned. So now we have to give a different style of bound that basically says that the collision probability remains more or less the same as before. It doesn't increase or decrease by too much. Okay, so and we don't need to go into the details of this bound more than that. But the algorithm itself is fairly simple, right? Because we just replace the Gaussian random projection by the FJLT random projection. So we can actually do better than this. Okay, and this is what we call and this comes from the same paper, and this is what we call the DH hash, right? So the components of this are a little different. So we'll have, let me define a few such notations. So we have the D, right, which is part of our randomized Hadamard transformation, which we have been using. We have a new matrix here called the G that we denote by G. What is G? G is again a diagonal matrix, except that it looks very similar to D, right, except that every entry is now sampled from an independent Gaussian. D was being sampled from independent plus minus 1, G is being sampled from independent Gaussian random variables. Each entry, each DII is an independent Gaussian random variable. We also have M, which looks like a random permutation matrix. So for a 3 by 3, for instance, it says that, so if you have a 3 by 3, it says that maybe this goes here, maybe this goes here, maybe this goes here, right? So basically every row and every column of M has only 1, 1, 1, and everything else is 0. So it's just, so M applied to any vector x just permutes the the values of the of xi, the values xi. And now instead of calculating this ax plus b, right, with a being PhD, this is what we do. So we multiply HD x, then we multiply again it by m, then we multiply it again by g, then we multiply it again by h, and this is my random projection first, and then we add a shift to it, and then we quantize. So you might ask that, okay, what is happening? Instead of multiplying it by a single A, we're multiplying it by more matrices now, right? So how is this any faster? Well, this is faster, right? Because although we are multiplying it by 1, 2, 3, 4, 5 matrices, right? 3 of them are diagonal, so multiplying by diagonal matrix is very easy, and 2 of them are Hadamard. So multiplying by Hadamard matrix is also very easy, right? So although instead of a single matrix we are now have multiple such operations to do, the overall effect is that it's actually much faster. And we can also so one thing now, okay, so one other thing to note is that, see, all these matrices are now d by d. Okay, so now we have this vector, which is actually a sort of length d vector, right? If I do HGMX this quantity. So what we could do is that we could sample k sort of indices from it. So we take one sample of k indices from it, that forms the index for my first hash bucket. We again sample k indices from it, that forms the index of my second hash bucket, and so on and so forth, right? So basically we're not redoing the calculation L times, right? We're just doing, taking multiple samples from here and then sort of calculating the index of each bucket, okay? And this turns out to work fine, right? And we can prove a similar theoretical guarantee for it, and the total calculation time for all the L bucket IDs now turns out to be d log d plus KL only, right? Which is again faster than the AC hash that we are doing, and certainly a lot faster than the original thing. Okay, so just to summarize, just to give some experimental results, you should look at the paper if you really want to read about this. What it says is that in terms of the recall, we are similar to the original LSH, right? But our query time and our average query time and our average time in actually calculating the hash buckets are both much faster than the original LSH, which is a win. Okay. So now just to sort of go forward, we have seen already one variant of the random projection, but there is more to come. right? So FJLT is fast, right? So definitely a big improvement. It's an amazing algorithm, right? But here's the problem, right? That I mean, it doesn't do well with a particular type of vectors that we are very interested sort of in machine learning related applications, and these are sparse vectors. For instance, if you're representing a document, and it's almost always a sparse vector, right? Because the size of the vocabulary is way larger than the actual number of words in the document, right? Now let's kind of think a little bit about what happens when I have the input x to be such a sparse vector and I apply random projections to it, right? Either I apply sort of multiplying it by a Gaussian matrix as we have been doing, or we multiplying it by PhD. What happens then? Okay. What happens is that in both cases it is becoming dense, right? Because Hadamard transformation makes it dense, right? And multiplying it by p again makes it, doesn't decrease the sparsity at least, and definitely multiplying it as a sparse vector by a dense Gaussian matrix makes it dense, right? So in both the constructions of random projections that we have seen, we are converting a sparse vector to a very dense vector. In fact, even if the original vector had a single non-zero entry, the final vector is likely to have all d non-zero entries, right? Basically full density. So it results in it's much more expensive, and this can become much more expensive in terms of both storage and computation. Okay, so here's the question: can we design a linear transformation such that it preserves the norm just like before, and it doesn't increase the density by so much, right? Maybe it has to increase the density by what, but maybe it doesn't increase the density by so much. Is it possible to sort of design such a random construction? It's not hard to see that the existing IID constructions don't satisfy this, and in some sense we've already seen an example before, right? When we were sort of talking about sparsifying the random projection matrix, right? That it's not that if I make the random projection matrix independently, and if I sort of make it very sparse, right? If I mostly try to put in zeros in every entry, then I'll end up with columns that are 0, and then I'll be in trouble, right? Because it's not going to preserve the norm of some vector. Here is another way of thinking about creating a random projection matrix. So think about creating think about a hash function first of all. So what does this hash function do? So let's say that the input vector x is of dimension d, right? So this is x, and y is of dimension k. So y is my target vector. So we have a hash function that goes from d to k, right? So basically it takes a coordinate ID. It takes a coordinate ID in d dimensions and maps it to one of the coordinate IDs, one of the buckets in k dimensions, right? We also have a sign hash function that does nothing but sort of adds that assigns a random sign to each of the dimensions, and so on and so forth. Maybe it assigns a plus here, minus here, plus here, and so on. Maybe it assigns a plus here. Okay. And now we obtain the vector y by basically taking all the entries that are being mapped into this bucket, multiplying them with the correct signs, with the appropriate signs. So in this case, for instance, a, b, and c are mapping into the second bucket of y. Therefore, the value that you put in the second bucket of y will be a minus b plus c, because s assigns plus 1 here, minus 1 here, and plus 1 here. Right. So this is what, and if you want to write it down formally, this is the definition of y. Right, and y of j is the summation over all I such that hi equal to j si times xi. Okay, so how does this correspond to a projection? It's not very hard to sort of see that you can capture this operation exactly by sort of designing a projection matrix. What does this projection matrix have? This projection matrix is again of dimension k by d, right? And what it has is that you look at every column, you sort of take the function h, and then for the ith column, you see where what is h of I, right? So h of I is a number between 1 and k. So you go to that column, you go to that particular row, and then you see what is si, right? Yeah, if si is plus 1, you put in plus 1 in that entry. If si is minus 1, you put in minus 1 in that entry, right? So basically, every column has a single non-zero entry. That non-zero entry is defined by the position of the non-zero entry is defined by h of I. And what you put in that non-zero entry, plus 1 and minus 1, is defined by s of I. Okay, and now it's not again very hard to see that sort of the operation that I just mentioned is basically the same as multiplying the vector x right, with this particular projection matrix. You get exactly the same y, right? So these two y's are the same, right? It's exactly the same operation. Just convince yourself of this. So a good thing has happened, right? Because now, if you again think of it, the number of non-zeros of y is not more than the number of non-zeros of x. Okay? Because I mean, if x has, I mean, right? Because every entry of x, I mean, falls into exactly one of the buckets. So therefore, it cannot increase the number of non-zeros of y. So now the question is that does the norm of y equal the norm of x? I mean, again, we're not going to go into why not, but it's not, I mean, just convince yourself, think about this a bit. But what we can claim is that norm preservation does not really happen if there's only one hash function. So we need to repeat this construction, right? And what we'll see is that, I mean, I'll just tell you what the construction is, and then we'll sort of talk about this, we'll sort of refresh this in the next class. What we need to do is that for every column, we were choosing only one non-zero entry. We are choosing only one non-zero entry. Here we'll have L hash function. Here what we'll do is choose L non-zero entries, L positions, okay, instead of one. Okay. So we'll make sure that every column has L positions more or less. Okay, and for each position, fill it up. I mean, toss a random coin again and fill it up with a +1 or -1. So similar to what SI was doing. Okay, so and we'll sort of go over the proof. We'll sort of talk about the. Let me actually finish this then. Then there are basically only two different ways of choosing these positions, right? One is that you could choose the positions with replacement, right? For instance, if I choose this position, then I could again choose back this position. So I choose L positions with replacement, which means that in effect there could be less than L non-zero entries, right? Because the non-zero entries could clash. The choice of the non-zero entries, and this was again work done in one of our papers. A better construction that was suggested by Kane and Nelson is that you choose L positions without replacement. Okay, so in every column you make sure that you choose L positions independently, right, without replacement, right, and every set of L positions is equally likely to come, and then for each non-zero position you put in a +1 or a -1 with probability half. So it turns out that you can make the same kind of guarantees. You can set k to be the same quantity, 1 over epsilon square log 1 over delta, some c by epsilon square, but this is order notation anyway. And if you choose L to be basically 1 by epsilon, right, you can choose L to be 1 by epsilon and then have the same Johnson-Lindenstrauss kind of guarantees. So now the number of what you can then guarantee is that now my projection matrix is much sparser, right? And what you can guarantee is that if a vector x has n and z x non-zero entries, now it will have at most n and z x by epsilon non-zero entries. So we have increased the number of non-zero entries by a factor 1 by epsilon, but still in effect it might actually have much less non-zero entries. It might not be entirely non-zero. It might not be complete dense. Okay. So just some references for this particular lecture. The fast Johnson-Lindenstrauss transformation, as you have seen, was the paper from Eilon and Chazelle. The two other results that I talked about, the application from locality sensitive hashing comes from this paper in KDD, and the sparse Johnson-Lindenstrauss transformation comes from this paper in Stock. And we'll see some applications of this later again. Thank you.